In this video, you people are going to study about the scalar point function definition, vector point function definition, and also scalar, what is a scalar field and what is a vector field. And also in the next cases, you people are going to study about the definitions of a divergence, curl, and also gradient, and finally directional derivatives. So first let us see what is the definition of a scalar point function and a vector point function. So before going to study a scalar point function and vector point function, let us see what is the meaning of a point function. What is the meaning of a point function? Okay, so consider a three-dimensional space here, x, y, and a z. In this space, consider a region R. Consider region R. In this region R, consider a point A with the coordinates x1, y1 and z1. Consider another one point B here. The coordinates of that are x2, y2 and z2. Okay, so what is the point function definition? So if the variable quantity, the value of that variable quantity, that is depends upon the position of the point. So position of the point is here A as a x1, y1, z1, and the position of this point B is here x2, y2, z2. Therefore the value of a variable quantity depends upon the points on which position it is. So this is called as a point function. So let us see what is the definition of a scalar point function and a vector point function. If to every point x, y, z of a region R in a space, there corresponds to a scalar phi of x, y, z, then phi is called as a scalar point function. Here, consider here again three-dimensional space as a x, y, and a z. In this three-dimensional space, consider a region R and point x, y, z in the region R. If to every point x, y, z in this region R under the three-dimensional space that defines for a scalar, then phi of x, y, z, that scalar is nothing but here phi of x, y, z, then this function phi is called as here scalar point function. Example for scalar point function as here x cube plus y cube plus z cube. Example for a scalar point function is here phi is equals to x cube plus y cube plus z cube. Consider, see here, phi is equals to x cube plus y cube plus z cube. This is the function, scalar point function. So consider this one as f of x, y, z generally. So put x, y, z as a 1, 1, 1, and what happens here? 1 cube plus 1 cube plus 1 cube, that gives here 3 only. This is the scalar. Okay, so let us see what is the definition of here vector point function. If to every point x, y, z of a region R in a space, there corresponds to a vector A of x, y, z, then vector A is called as here vector point function. Again same case here, consider a three-dimensional space. In this three-dimensional space, consider region R with a point x, y, z. If every point x, y, z of a region R under the three-dimensional space, there corresponds to a vector. If the point is defined for the vector, that vector is nothing but here vector A of x, y, z, then this vector A is called as here vector point function. Then this vector A is called as a vector point function. Example for a vector point function, consider here f of x, y, z as a vector A is equals to x square I plus x, y, z plus z square k. Consider this example. This is called as a vector point function. How? See here, consider x, y, z as a 1, 1, 1, then vector A, what happens here? 1 square into I plus 1 into 1 j plus z means 1 square. So that happens here I plus j plus k. Observe this one, this is the vector because it contains the directional. Direction means I, j, k. This is obviously vector. Okay, so this is called as a vector point function. Example for a scalar point function, phi is equals to x cube plus y cube plus z cube. You can take any example. And vector point function example, vector A is equals to x square I plus yj plus z square k. So what is the difference between the scalar point function and vector point function? Consider this one, vector point function x square I plus yj plus z square k. Here the function contains here I, j, k terms. What are I, j, k here? Unit vectors. So along x-axis, y-axis and z-axis respectively. So consider this one x cube plus y cube plus z cube. This function does not include here I, j, k. Then it is obviously scalar. There is no direction here. Obviously this is the scalar. Here I, j, k terms is the, means it includes a I, j, k. Obviously this is the vector. Okay. So what it means here, in future wherever we use here, in future whenever we denote a phi, that phi is always a scalar. Okay. Similarly vector A is always here vector quantity. Okay. So next let us see the next definitions. Before going to study definitions of a gradient, divergence and a curl and also directional derivatives, let us see what is the operator meaning. Okay, so what we have operators, there are two type of operators in your syllabus. First one is the vector differential operator, next one is the Laplacian operator. Okay, what is a vector differential operator? The vector differential operator is denoted as here delta. Okay, del. Read it as a nabla or a del here, and is defined as del is equals to dou by dou x into I plus dou by dou I into j plus dou by dou z into k. It can also be written as summation of dou by dou x of I. Okay, vector differential operator, it is denoted as a del and it read it as a nabla or a del. Okay, left to you. So, and it is defined as a del is equals to dou by dou x into I plus dou by dou I into j plus dou by dou z into k. Okay, this is an just operator. Unless and until we operate on the function, it has no meaning. It is just act like a operator. Similarly, we have another one operator, that is a Laplacian operator. The Laplacian operator, it is denoted as a del square. It is denoted as a del square and is defined as a del square as a dou square by dou x square plus dou square by dou I square plus dou square by